Hi, today we are looking at circular motion. So with the circular motion we'll be focusing on, we'll be looking at dealing with uniform circular motion. So that means that as an object travels in a circle, it is moving at a constant speed. So the magnitude of our velocity will always be the same, but because we're changing direction constantly, our direction would change for our velocity. Now, our velocity at any given point will be tangent to the circle the motion creates. Now, for our speed, or the magnitude of the velocity, we'll modify our basic uniform motion speed equation where we had our speed was distance traveled divided by time. Now, for this, we are going to replace our distance with the distance to go around a circle, and our time with a period to travel the circle one time. So essentially our distance gets replaced with 2 pi r, and our time gets replaced with our period. So our speed is equal to 2 pi r divided by our period. Using this in an example, a satellite is in geosynchronous orbit. This means it remains above the same location of the Earth. It is at a distance of 1.8 times 10 to the 7 meters from the center of the Earth. With what speed is it moving? So let's start by writing out the information that we do have. We know our r is 1.8 times 10 to the 7 meters. We also know our period is 24 hours, which, if we convert into seconds, is 86,400 seconds. And we're trying to solve for the speed. So we've got our speed as 2 pi r over our period. In this case, we don't have to rearrange it all. We can just substitute directly in. And then calculate and round to appropriate significant figures. We end up with a speed of 1,300 meters per second. For circular acceleration, even though our speed remains uniform, because we have a constantly changing direction, we have an acceleration. Now, this acceleration is referred to as the centripetal acceleration and is always directed towards the center of the circle. Now, our equation for this is our acceleration centripetal is our speed squared divided by our radius. So an example, a merry-go-round at an amusement park has a diameter of 20 meters, and it has a period of 1.5 minutes was its centripetal acceleration. So I'd start by writing out what we're given. We're given our diameter. We know our radius is half of that, so we know our radius would be 10 meters, and we are given a period of 1.5 minutes. We know we need that in seconds. 1.5 minutes is 90 seconds. So we can substitute our equation for our velocity to solve for our velocity and then get our acceleration. So we've got our velocity or speed is 2 pi r over our period. Substitute our values in, and we get a speed of 0.698 meters per second. Use our centripetal acceleration equation of speed squared divided by r. Substitute our values in, and we get a centripetal acceleration of 0.049 meters per second squared. Now, there is a different way we could have solved this, which we'll talk about that on the next page, and that would be essentially combining our speed equation with our centripetal acceleration equation. So since we know that our speed is 2 pi r over our period and our acceleration is our speed squared divided by r, we could substitute our speed equation into our acceleration equation. We'd then square what's inside our brackets and rearrange and simplify a bit more, and we get our centripetal acceleration is equal to 4 times pi squared times r over our period squared. Now, if we have centripetal acceleration, we can also have centripetal force. Now, since our acceleration is always directed towards the center of a circle, that means there must always be a force towards our center. Now, that force is our centripetal force. It's the force that's causing our circular motion. Now, depending on the situation, it can be caused by a tension force. So, for example, if we're swinging something in a circle attached to a string or something like that, it can be caused by a force of gravity. So, an amusement park ride right at the very top, force of gravity would be pushing something towards the center. We can have a frictional force, so the force between tires and a road are providing that centripetal force. Now, our centripetal force is essentially calculated using our basic force equation from physics 11 of sum of forces is mass times acceleration, with, in this case, our acceleration being our centripetal acceleration. And we can also write that out by replacing our acceleration with v squared over r, or with a 4 pi squared r over our period squared. So we'll look at an example. We have a car of mass 1,200 kilograms takes a corner of radius 150 meters at a speed of 15 meters per second. We want to know what force of friction is keeping the car on the road. So in this case, our friction force is causing our centripetal force, allowing the car to turn. So writing out what we have, we know our mass is 1,200 kilograms. We know the radius of the corner is 150 meters, and we have a speed of 15 meters per second. So we can calculate our centripetal force as mass times our acceleration. Now, our acceleration in this case, given what we have been given, I would use v squared over r for it. At this point, substitute our values in, and we end up with a force centripetal of 1,800 newtons, which is our force of friction in this case.